Okay, yeah, we can go.
Okay. I guess everybody is in for the last session. So I'm going to talk before Fedor he starts talking about how to structure estimate dynamic games for multiplicity of the equilibrium. I'm going to give a kind of start easy. Just take the simplest possible case of a static game, and then run through different ways to estimate that and some of the challenges, because it's fine with just a little simplicity, and then you'll get it. Okay, so we've been throughout the week, bunch of different methods to estimating games, and here's some of them. Okay, so you can do it roughly. You could do like two-step estimators, as a whole variety of two-step estimators, not only for static games but also for dynamic ones. You go out and estimate the CCPs, you plug them into the best response mappings, you hold that fixed, and then if it's a dynamic game, it boils it down to something just essentially be a static problem, and then you are also holding fixed beliefs about what everybody else is doing. So it's simple, to do your locate or your least squares. Then that has issues with finite set of properties, and I think in year 2007 and 2 in the case of static games, single agent games, propose this recursive way of updating. And there's a more recent one by one of the theories called the efficient supervector. That's imposing that zero Jacobian property. So it's equivalent to that like that it's both more stable. And so NBL could be a little bit unstable. So there's the papers fighting that, and so you might ask, why would just not do a maximum likelihood? And the problem is we need to be able to solve for all macro perfect equilibria if it's dynamic games and all the triangle irregular. NPAT is potentially a solution. There you don't really repeatedly do it as you search over the parameters. Really only these constraints you to hold it in. So why don't we just compare and see some of the challenges with these estimators. That's the purpose of the whole lecture. We're going to come back to do it for a particular dynamic game in the end, but I just want to illustrate some of the challenges that arise in this very simple game first. Okay, so very, very simple. This is good. You have two firms, A and B, and they're just deciding whether or not to serve them out. Okay, so one. Okay. So PA that's equal to 1 if firm A is choosing to enter into the market, it's 0 otherwise, and DB is going to be equal to 1 if that's something. Okay, so here's some exposed payoffs for the two functions of the two firms. So we can normalize the payoffs, except normalize the payoffs to these epsilons if you're not serving the market. And guess what? They're going to be at extreme level. And otherwise, you're going to get alpha if you're alone. So that is if you're holding number there, D is equal to 0. And otherwise, you're going to get these duopoly profits. So that's essentially going to end with beta, and then you multiply with X, which is kind of outside the fact. It's kind of like a different firm types. So, and then there's like a corresponding set of payoffs for the other firm. So it's like it. And then depending on whether alpha, the size of alpha and beta, the size of these monopoly profits and duopoly profits, this could be like a coordination rate of coordination. So what we want to do is we can see, can we estimate these structural parameters given information about these discrete choices? Okay? And now if you have, explanatory variables like X, you will see how they vary with the explanatory variable. We're going to keep it even simpler than we're just going to say, okay, let's just, X is just fixed. Okay, we just have the data of 30. Okay. So this is just going to be observed common knowledge. The epsilons, well, they're private information, just like everything else has been so far. So they are observed not by the econometrician, not by the opponent, but only the firm that's making the decision. And we can assume that they are ID tree values, so it's my logical. And then you can back out what the best response functions are. They are essentially the probabilities for investing or for entering the market as a function of the opponent's probabilities that are following these logic forms. You're taking expectation over what is the other guy doing when deriving its optimal best response methods in terms of conditional choice probabilities. So these are just logic forms. And so we can draw them for, X is fixed, we just fix them like this. We draw them in a box, and then we find equilibrium. This is how we find equilibrium, right? That's when these two probabilities are mutual best responses. That is when the two best response functions are satisfied at the same time. So it's just a simple set of two nonlinear equations. We can do that. We just need some numbers. We'll put beta equal to -11 and alpha equal to 5. Okay, so if you're alone in the market, you get 5 times whatever X is. If you're there together with your opponent, you really get like knocked over, right? You get like negative profits. Okay. So how does that look? Looks like this. So here's our best response mappings. Okay, you got the best response mapping for firm A, that's a red one. So whenever let's take the other one. That's a function of the probability of investment for firm A. That's the best response of firm B. We just have our logic formula here plotted, so we can plot it for different values of that investment probability. That's just that logic form, and then we turn the axis around and plot the other one. That's with very PB. We kind of have these two best response methods, functions in this case, and then with the free equilibrium. Okay? That's kind of that's a world we're in. There's 3 solutions. We have 3 equilibrium. So we want to see if we can estimate those alphas and beta. I'll just pick a particular one here. 5 and -11. Okay. Now Econometrics is the other way around. We start with the data and we try to see if we can estimate these parameters. Now all of a sudden more things can happen. You can also have different outcomes because of multiplicity of equilibrium. So can we still estimate these parameters? Okay. Now in order to be able to find these different equilibria, we need like an algorithm that can solve for this one. So I'm going to do something very simple here. I'm just going to substitute one into the other. They call it like the second order best response function. And that's what we have here. So this is second order best response function for firm A. And you see here we have like 3 fixed points, okay? Corresponding to the investment probabilities of firm A in these 3 different equilibria. So there's clearly an equilibrium where it's not very likely that firm A is investing, probably because firm B is investing with a high probability. So this is like firm A's investment probability and then higher investment probability from B in that case. So then that's another equilibrium. Okay, so we can solve all these equilibria pretty easily, right? Let's see here. I mean, we could start doing successive approximation, right? Just guess an equilibrium, put it into the best response function, and bang, we found the solution. And the problem here is that this best response mapping is not a contract. It depends on where you start. So, well, I could also start here and we'll find the same equilibrium. But the problem is if I start here, is I find another solution. Okay, and how do you find the one in the middle? That's unstable. You can't do that by successive approximations. And that's how we solve. Normally, we solve the dynamic models by successive approximations on the Bellman equation. So imagine you do that with the Bellman equations. Just iterate on that. It's no longer a contraction, right? Because of a contraction, there will be one solution. Okay, that if it's a contraction mapping, there's a unique fixed point. Not the case here. We have multiple solutions. So iterative solving on the Bellman equations or the best response mappings going to give you different answers depending on where you start.
I have a question.
Yes.
You're talking like there's 3 equilibria. How do you know that?
Well, I can see that
Why not 5?
because I mean, how I can prove they're not fine. Well,
I mean, 5 would be much harder to compute, right?
that's right. I mean, I cannot rule out that it's fine. But here it's actually a trivial algorithm to find them even in the case of 5. Right? You can start here in the corners, and then you're gonna kind of trap the equilibrium in between these, and then you can do a bisection to find the nearest equilibrium, and then you're gonna find one, and then you kind of divide that interval into you take that interval, do successive approximations, and see if there's more equilibria in there, and then you can kind of build the full set of equilibria based on a combination of bisections and successive approximations. So it's trivial to solve this.
Oh, it's likely there's only one variable.
Yeah. There's only one variable. That's another thing. Okay, now this is a scalar value. Good luck with your Bellman equations, right? You have all the different states, and then that multiply with the number of players. So you got this cursor dimensionality. It's going to be twice probability is huge. Here's just a number, right? So that's very easy. Okay, so I want to move on. Okay? So let's take a look at it. Let's see if we can do some Monte Carlo. Now we know we can solve this game, right? We can solve for any equilibrium and generate data from each of these 3 different equilibria. So that's what we're going to do. So, data generating processes, data is generated from this model, and we just pick an equilibrium, and then we just simulate the data. Okay, we can do that. We know what the investment probabilities are, so we just split in a bunch of columns. Okay, with these probabilities. Okay, so we're going to do that 1,000 times, and then given the data, we want to see, can we recover alpha and beta? So let's start doing maximum like that. We do maximum like that? Well, here's a likelihood function. It's pretty trivial. It's like the indicator for investment times the log of the probability that you are investing, which is functions of the parameters. If you're moving around those alphas and betas, it's going to change those locus formulas, so it's going to change where they're crossing. Okay? And so then you got to play A, the probability that play A is not investing times the indicator that it's not investing. And you could do the same, you add up for all the different players. That's a likelihood function. What is this? Well, these are the solutions to these Bayesian-Nash equilibrium equations. Now, see, here's a problem, right? We just agreed that there could be multiple solutions here, right? So what do, right? You need to take the max over each of these different equilibria as well. So, how do you do that? We could do the nested fixed point algorithm. We search over, just like we do with Harold-Sugden, we search over the parameter space to maximize that likelihood function, and then for every given value of alpha and beta, we solve the model. Okay? That is, we solve for all these 3 different equilibria, and then we're going to pick the equilibrium that gives the highest likelihood, and then plot that likelihood function. Now it suddenly becomes like a function of alpha and beta only, right? If you just take that upper interval. Let's take a look at how that looks. This is the likelihood function from this model. Okay, so you got alpha and you got beta. This is a true value. And you got the parameter estimates, the maximum likelihood estimate, very close by, right at the top. Okay? This is 3D, so it's hard to see. But if you were turning this around, you'll be able to see that this is actually the top and not right back in the picture. It's okay. Okay, so let's move on. So what's going on here? This is the equilibrium. This is a likelihood function with data is generated from equilibrium number 1. Well, what about this guy? This is equilibrium number 2. Does it look like your favorite likelihood function? What's going on? What do you think is going on? What happens? So I'm calculating the likelihood for these different combinations of alpha and beta, just plotting them. What's going on? This is this cliff here. What's happening? What? The equilibrium changed. The number of equilibrium has changed, right? So if you look at this guy here, what's happening is when you move around alpha and beta, these curves are moving around, and we were generating data from this equilibrium, and all of a sudden, that equilibrium doesn't exist anymore, right? And you're trying to use these numbers inside the likelihood function to kind of, you want these are the numbers that we use to generate the data, and you want those to be as close as possible to those the model predicts. But now the model cannot predict this combination because it's gone, right? And then you see this huge drop in the likelihood because the only thing that's left is this equilibrium down here, right? Because now these are no longer. So you get a huge discontinuity in the likelihood function. Oh God, I'm not used to that. Okay. What do you think about equilibrium number 3? How do you think the likelihood function will look? Will it look like this one? Or will it look nice and smooth? It was a stable equilibrium. Yeah. See what happens here is you change parameter just a little bit, right? And then the equilibrium was knocked out, but it's not knocking out only one equilibrium, it's actually 2 equilibria, right? It's both equilibrium 2 and 3. So we're going to have something similar to this. Now, all of this is pretty daunting, right? Because how do you maximize the likelihood function? And how do you get inference out of that, right? You want, your standard theorems for maximum likelihood and asymptotic inference and all that is kind of assuming that objective function is differentiable and continuous, and doesn't look like it's okay. Computationally, it's hard, but you can do another approach, MCAT. Right? That is the same thing. Now we maximize this, what's it called, like the pseudo likelihood or the extended likelihood. I forgot the last name, but this thing where we let it be a function of the probability. Okay, so you can't do that, right? Only and then expect to be able to estimate both alpha and beta and these PA and PB in the constraint optimization problem. We'll lose identification. So we need to impose the constraints, and these are just going to be these Bayesian edge equilibrium constraints formed by the best response line. Okay, so we can do that and solve it by constraint optimization. So before we had like an unconstrained optimization problem because we repeatedly solve for the equilibria for each trial value of the parameter. Yes?
Question. So you said that we have to maximize likelihood over the set of equilibrium.
Mm-hmm.
But in this formulation with empathy,
Yeah.
does it do the same thing?
No, it's just imposes the constraints.
So how does it choose the max? How does it choose the maximum likelihood?
Well, in principle it does, right? Because it's maximizing that likelihood function not only with respect to the parameters, but also with respect to the to the equilibrium or the equilibrium choice probabilities. Okay, so, but then you will need to do a global search over all the different values. Right? And so that's the problem. This max is not just easy to implement because you have like a set of three equilibria. So you in principle have 3 equilibrium specific likelihoods that are separated. Okay, so you would have to like discontinuously jump from one to the other. Once one constraint is satisfied, how do you jump out of it? And that's kind of corresponding to like local minima and a local max, also the maximum, like the local maximum on the like be trapped in that. Okay. Anyway, you can do it in this simple example. It's not hard to find the maximum, and so we're gonna do a little bit of Monte Carlo instance. And there's just some other ways. I just want to give for the Fedor purchase. This is just a reminder. How would you do it in the simple example with these two-step estimates? So you could do like, yeah, you can do this doesn't overestimate flavor with the least squares, or you could do pseudo maximum likelihood, and you could do many different objective functions. The idea is you go out and estimate these conditional choice probabilities from the data. Maybe just use a frequency estimator, the number of times firm A and firm B did the investment. That's your conditional choice probabilities. You throw those right into those best response mappings. Okay. And then you vary the structural parameters, alpha and beta, until these constraints are satisfied. Minimize the distance in this case here, or you could do pseudo maximum likelihood. Maximize the pseudo likelihood with respect to these parameters. Now everything is fixed. You don't need to search for the CCPs anymore because you calculated them from the data. And no problem here with equilibrium selection because we've just estimated those equilibria in the data. This is very easy. Problem is, if you are in a game world with dynamic game, with many state variables and many players, these are huge objects. They are no longer just scalars, right? So this, maybe you have like 1,000 observations that want to estimate like 1 million probabilities. So how do you do that? That's a problem. That's the Achilles heel of the two-step estimator, right? Is that there's a cursor dimensionality. The cursor dimensionality involved in either solving the model, that would be for NFXP, the issue, or the cursor dimensionality in terms of non-parametrically estimating all these conditional choice problems. So that's a problem here. You get finite sample bias. You get bias, right? Because these Bayesian-Nash equilibrium equation, who says there are any values of alpha and beta that satisfy these when you're putting in your frequency estimates of the CCPs? That's why there are these recursive updates that improve and gradually impose more and more structure from the model. It's like Victor done with the nested pseudo likelihood, and this EPL that would do a different type of iteration. It would not do a successive approximation on the NPL mapping. It would do like more like a Newton iteration. Anyway. So, just to set up Fedor for the challenge here is here's some remarks about these different estimators we've been through the week. The implementations of maximum likelihood, well, that's just efficient and the model is well specified. You're going to get unbiased estimates, but it's just computational pretty challenging, right? Because you need to compute all equilibria for every trial value of the parameters as you search over the parameter space, and there'll be multiple one of them, and you need to take the max over those. Okay. And then you need to find the maximum of this discontinuous likelihood. MPEG, well, maybe computational lighter, right? Because your objective function and constraints are smooth in each of its variables, the structural parameters and the conditional choice probabilities. The constraints, they're just logit formulas, right? And the likelihood function, well, that's also a smooth thing, unless you impose that the equilibrium should hold, right? Because that's where you change parameters and suddenly equilibria are disappeared. Okay, so it's smooth. And it has the benefit that it satisfies the constraint. It should only satisfy the constraints at the optimal, but you might get local min. So that's giving us some problem. Unstandard. Two-step estimators, computational very fast, but they are inefficient and biased in small samples. In this case, maybe not so much because we're just trying to estimate two scalars, PA and PB, but in a dynamic game, you know, it's a whole function you want to estimate non-parametric. And that's why, you know, this debiasing Whitney was talking about, it's like a first order importance, trying to deal with that problem. Okay. And the best response mapping is not satisfied. That's why you get that finite sample. Model is not important. And then NPL and EPL should bridge the gap. NPL can be unstable in games for multiplicity and equilibrium. Essentially, you're doing successive approximations, right? On this, we call it the NPL mapping. And NPL mapping is like the two-step estimator, right? It's producing predicted choice probabilities from the two-step estimator. You throw those CCPs right back in, and you do it again and again and again. It's like a successive approximation. If that should converge to one unique thing and the maximum likelihood estimator, well, it needs to be a contraction. We are relying on contraction problem. It's not, right? It will be multiple. So this is very critical that you have very good starting values, and that you might have good starting values via good CCPs to begin with. EPL is doing a little better on that because it's not relying on the contraction problem. It's more doing like a Newton iteration, so it doesn't diverge away from the Okay, I'm gonna stop here and like hand over the floor to Fedor and just see how to do estimation of dynamic games, what multiplicity of equilibrium. Now you've seen three. Promise you, Fedor will show you more than three equilibria once it becomes a dynamic game.
All right. What's on the other slide?
Oh,
So I switch here, right? Right. So, can you hear me? What did we learn from Bertel just now? The takeaways that I noticed, or I take with me. First, multiplicity of equilibria is something that is real. Okay, it exists in problems. Computing multiple equilibria, it requires additional effort. And it can be possible, but in general, it's kind of hard. And then, you know, the likelihood that we are working with when we estimate these models just intrinsically has discontinuities or may have discontinuities due to the multiplicity of equilibria. So if you're unlucky that the data generating process, the data generating equilibrium just disappears when you move parameter away, that's when you will have the cliff. And whatever estimation method that you're using for that problem of yours, we'll have to deal with that somehow. And so, you know, the methods for estimation of dynamic games, or for games for that matter, that we are using hopefully work, right? Hopefully there's a unique equilibrium in your model. It takes an analytical proof and it takes additional work, which usually we don't have time for, to actually show. But if you can, that's extremely valuable. If you can analytically show the you know, what's happening with the equilibrium in the model. Yeah. So then, if you want to really, you know, do the NFXP, and this is kind of the world that we are trying to remain in. I mean, Bertel and I. There's a lot of value in that, right? Because if you are able to solve the model completely, then counterfactuals will be most important. And then maybe we can, you know, learn to solve particular model. Okay, let me start. So in dynamics, things are much more complicated. Here's the ambition. I first want to talk about solving dynamic games. It turns out that there's this class of games which has the directionality property that you can solve in principle for all solutions, even though there can be millions of solutions. Okay, and I want to first talk about that. It's hard, but it's sometimes possible. We will talk about a particular game, Bertrand pricing investment game, that I will set up. Believe me, it's motivated by a very practical example, a particular industry in a particular country, a particular collusion case. But I will not talk about it now. We'll just jump into the mathematical formulation. But I can talk about that later if you want. We will be able to solve it once using an algorithm called state recursion, or once for one equilibrium, and then we will be able to solve it for all equilibria by repeatedly applying that algorithm. And then I want to talk about structural estimation of these games, keeping in mind that, you know, the idea of full solution maximum likelihood. And, you know, why are we doing this? So far, we're doing it basically to break all other estimators, right? That's the kind of the secret here. We really want to have a test bed for the estimators that people actually use in empirical work and see what are the boundaries of their applicability. And so we successfully break everything, and our estimator turns out to be robust to multiplicity of equilibria, even though it's pretty hard to implement and probably has to be implemented in, not probably, but has to be implemented, you know, for each model in a particular way. I will talk about the general principles though. This is a super long project. So I don't know whether you want to know that, but sometimes projects take, what's it, 16 years now? It did produce a couple of papers, don't get me wrong, but this third paper is taken particularly long. So we have a paper on solving the game, a particular game. As I said, this is motivated by a very practical example. So we have a separate paper in IER just talking about that particular setup, and we actually prove theorems. So there's some analytical proofs that we are able to do on this game once we solved it many, many times and kind of understood how the solutions look. And now we are finishing the paper on estimation and running this Monte Carlo to test different estimators. Let me just jump into this. This is the simplest possible extension of a Bertrand price competition that we could think of, or we could try to set up. We're going to have two firms, no entry and exit, infinite horizon, discrete time. Yeah, they obviously maximize expected discounted profits. In each time period, there's going to be two choices, okay? One choice is a price for the product, and for simplicity, we will assume homogeneous product for now. And this is just Bertrand. Consumers, I don't know if I say it somewhere. Yes, consumers, continuum consumers, they were going to make just static purchasing decision. So this pricing decision is going to basically decide the profits in each particular time period. And because consumers are static, firms will also be static in that particular choice. That actually gives you the formula for the revenue sort immediately, right? We make a normalizing assumption just to have the profits, the one period payoff for the firms to be a difference between the marginal cost of production of these two firms. If your cost leader, then you're earning this in a period. If you're a cost follower, then in the price competition, the price falls to the highest of the marginal costs, and then this guy earns nothing, right? If you're a follower. And so the whole interest of this dynamic process is going to be in the second decision. The second decision works like this. It's the simplest possible. It's a binary choice of whether to improve your technology or not to improve your technology. And technology is going to be improved or not in terms of the marginal cost of production. And so we're going to have the state-of-the-art production cost process. Imagine that firms here are not doing R&D. They are just using the new technology when it becomes available. So this C is going to describe R&D done somewhere else outside of this market or this industry. And at any time, they can just decide to buy the new technology and reduce their marginal cost of production. And that's going to be costly. This is going to be costly. And what they will know is that there's this exogenous Markov process, right? So they will have beliefs about how the new technology is improving. And these beliefs will be described by this phi, conditional probability or transition probability. the space will be discretized with n points, and so each company can be on one of the 3 points in terms of production, marginal cost of production. Now, this is very important observation here. We're talking about the technological progress, right? Somebody else is improving technology, reducing marginal cost. Once something is known in this technology, it's very natural to assume that C will not go back. And that's what this says, right? For CT plus 1 greater than CT, the transition probability is 0. So this state-of-the-art technology can never go back to higher levels of marginal cost. And that's all. And so now what's the state of the game? What is the important information that the firms have to be keeping in the back of their minds? That's basically C1, C2, and C, where C1 and C2 are current marginal cost of the two competitors, and this is the state of the art. Nobody can be in front of the state of the art, right, by definition. And therefore, we also have this additional inequalities. This is going to be observable actions and private information in terms of the extreme value shocks in the tradition of this whole week and discrete choice literature. Now, you probably noticed on this slide that there are going to be simultaneous or alternating moves in this purchasing decisions of the new technologies. I will mainly talk about simultaneous move, but we also consider a problem where the firms alternate and actually stochastically alternate in the order of their moves and see how that changes the set of solutions. Okay, let me talk about Bellman equations. And of course, they will have all of the information you need to know about this model. So the value function in particular states of the industry for firm one with particular private information is just a max between two things, right? They can invest or they don't invest. So this is denoted by I and N. The choice-specific value functions are given by the profits that they get today. And as you can see, these are independent of their actions. We assume there's one period time to build. If they decide to invest in the technology, their current profits are not changed. What's changed is that they have to pay the cost of buying this new technology, and their future is going to be different. Their future is going to be decided by whether they've invested or not. You know, already from this structure, we get the choice probabilities, and you can write the same things for the firm too, right? Symmetrical. So what are the expected values? Well, it's essentially an integral over three things. First of all, did my competitor invest or not? This is written for firm one. The expected value in the case when they did not invest will imply that their tomorrow will have C1, the same level as they have today. If they invest, then their cost tomorrow will be set to C, right? So the current state of the art. Now, depending on whether my competitor invested or not, their cost is going to be C or it just remains at the level C2. The same thing here. I have to take an integral, or it could have been written as a sum over what the state of the art can do between today and tomorrow. And finally, you have this H function, which is basically the expectation of the maximum utility that I get from my own choice tomorrow. Right? So our normal log sum. That's it. That's the model. Can you know, if you close your eyes and kind of think for a little bit, you should, you know, get a picture, a mental picture of what can happen in this game. This is the simplest possible extension, as I was trying to say. And the Bellman equations fit on one slide. You know, okay, let's see. Well, I'm going to switch to pictures. Right? This is the last lecture. This is the state space. It's going to be discretized. Has three dimensions: C1 to C and C, C1, C2, and C. I'm going to plot the state of the art on the vertical and the cost for two firms on the horizontal axis. You know, if you think about different levels of this pyramid, this corresponds to different levels of the state of the art. And so the problem will be bounded, you know, at the top of the pyramid, that's when everybody has the same state of the art cost. This is where we kind of start, right? Because things then can happen afterwards. And if you look at the lower levels of this pyramid, none of the firms can be in front of the state of the art, and therefore you have this expanding kind of space in terms of the different layers. So it's not a very large firm. Let's think about the dynamics, what this model describes. Imagine that we started at the top, there was probably a technological improvement at some point, and the whole system, the whole model kind of fell through to the next level. And at that point, firms may have invested in this new technology that became available. Imagine that invested in the same time. They can do it. It's a simultaneous move game. This is very unfortunate, right? Because now that this whole system transitioned to the point where both firms have the new but same state-of-the-art marginal cost, nobody's earning any money, right? They have the same marginal cost. The return competition brought the price down to that level. They shouldn't have invested. This is kind of the coordination failure example. Okay, well, the system could have stayed there for some time without any change. But at some point, there was another technological improvement, and I'm drawing this with just one step. It could have been fallen down a few steps. That's also totally allowed. And here, for example, it just happened that one of the firms invested. And also, I don't know, maybe the system stayed on this point for some time. Time is kind of independent of these transitions. They could have stayed here, and I don't know, drew some, both firms drew the idiosyncratic shocks that prevented them from any investments. But maybe one of them invested and the system transitioned here. This is when one of the firms has the state-of-the-art cost, low cost, and the other one is not yet, right? Has this distance in terms of the costs. And that means that one of the firms is now earning some profits. And for some time, the system could have been in that state. Maybe, it could also move here if the second firm invests. But imagine there was another technological improvement, we fell through to the next level, and this other firm invested, okay? And now the leadership changed. Now the first firm, if that was second, say this is first, is now a cost leader, and they this is the event of the leapfrogging. As time goes by, the costs, the marginal costs that characterize the industries, the firms can kind of leapfrog over each other in this dynamic coordination process. Now, maybe for some idiosyncratic reasons, the second firm also made the investment, and the whole industry transitions into this state. Well, this is a very interesting state. Imagine that the progress went so far that this is exactly at zero, right? The marginal cost of production just fall into zero. And they're both attained that level. Now, nothing can happen in this world anymore. This is a completely absorbing state. Of course, it doesn't have to be exactly zero, but there's going to be this point where no further transitions in terms of the cost of productions are possible. That's an absorbing state. We're going to use that. The fact that this is a non-stationary process on finite set of points in the state space that has an absorbing state or a set of absorbing states, this is going to be the key for solving the whole problem. Okay, so let me put it into more general terms and move away from the pyramid to go to the plane. These are now different layers of the pyramid, and I've just drawn transitions that correspond to the improvement in the state-of-the-art technology. You can see that each error here crosses the boundaries between the layers, right? These are all possible changes of the state of the industry because of the technological improvement. Okay? I can draw strategies in the same graph. Let's assume that firm one invests in all interior points. And interior points are those yellow points where both of the firms are behind the technological frontier. If I just want to illustrate a strategy, I'm just simply adding some errors. Maybe firm two invests in all edge points. Edge points are blue points. Those are the points where one of the firms is at the technological frontier and the other is lagging behind. And so, look, for a given strategy, we have this graph that represents a partial order on the set of points in the state space. Now, I'm going to be interested not in just one strategy. I want to think about all feasible strategies. And in order to illustrate it in a graph, I can basically just add all transitions between the points in the state space which are possible under all actions in each point of the state space. And that would basically cover all of the strategies that the firms can play in this structure. Okay, can you see something special about this graph?
What's a red dot at the end?
Yeah, that's that absorbing state where nothing else is changing. All right. Well, if you were computer science students, and maybe some of you know about this, let's run an algorithm which is called topological sorting on the graph. And that algorithm is very simple. It basically calls you to do the following. Let's find all of the dots, all of the vertices in the graph that do not have any outgoing transitions. And we have only one of those dots. It's right here. We're gonna combine all of those points into a subset, into a group. We call it a stage in the paper, and delete all of the connections to that vertex, or to those vertices. And repeat the step. Now we can identify all of this as being absorbing, put them into a different group, do the same, and continue this topological sort until we get here, right? And look, our complete graph got sorted. There is nothing else left. That didn't have to be like that. It could have been that we were in a situation where some vertices were connected in a way that you couldn't get, you couldn't choose those which don't have outgoing connections. Can you imagine that? The prime example is a cycle. If you had a cycle in the graph, then this algorithm would not finish in this way. There would be a situation when there is a graph and no vertices can be chosen as those without outgoing connections, right? In the cycle, every vertex would have an outgoing connection. We don't have that. Well, that's a clear indication that the game belongs to the class of directional dynamic game. If you look at the paper, the definition is more formal, but that's essentially the idea. So if we can sort the vertices in this graph, in this game graph, representing all possible transitions in such a way that we discover the absence of cycles, which basically means that the game graph is a DAG, directional acyclical graph, although this is not quite right because we're allowing for self loops. DAG cannot have self loops from the vertex to the vertex. So it's a DAG with a star. Right, so the fact that the graph is a DAG and the topological sort finishes in a full partition of the state space and the game is DDG are all equivalent statements. Okay, so we want to think about this DDG game, the games which have this inherent directionality to the transitions over the state space embedded in them. Okay, why is this interesting? Well, let me put all of those stages, all of these subsets that we've defined in the topological sort, and back impose all possible transitions. You can see that we essentially have a fully sorted partition of the state space. Right? The game starts wherever you choose. The game can only go in that one direction. Can you see that? And this is true for any directional game that is represented by a DAG. Okay, what can I do now? Well, I can essentially do backwards induction. Let me start with all of the points which are absorbing. The transitions through time are still possible, but because this is just one point, or maybe several points, there's no transitions in terms of the change of the structure of the industry. And so it turns out that solving this game, even though it's infinite horizon, is actually pretty simple. I think this one has an analytical solution. Right? Once I solve the game here, and what do I mean by solve? I mean computing choice probabilities for all players in this point and value functions for all players in this point. I can move to the points that depend on the value functions here. If you think about Bellman equations, we have in the expected value in the right hand side, we have some expressions which involve value functions here, right, to describe the options on the previous point. And so once I have the solution here, I can easily solve these. They're all like static games now. And then I've solved these guys, and I can move to the next stage. And so this is basically a backwards induction that happens over the transitions among the points in the state space. Is that clear? So this is basically just the generalization of backwards induction. Now, this doesn't have to be about dynamic games. You can use this idea everywhere where you have directional transitions. So even if you're not interested in games or estimation of really complicated models, this is an idea which might be useful just by itself. In finite horizon problem, we have time transitioning from t to t+1 in kind of very simple DAG. You can actually allow for much more complicated transitions. Okay. Now, this slide here should remind you of this representation of the integrated value functions, which I think Victor used and proved in the third lecture. This is really important for the two-step estimators, because this is the expression that gives you the value function, the model part that expressed through the choice probabilities and the immediate rewards, right, which can be also represented as functions of choice probability. This is the correction term, which is also a function of choice probability. Anyway, this is what you need for Huxley inversion. If you write the Bellman equation in this representation, you have this transition matrix F entering the expression, and it just turns out that in directional games, this transition matrix F can be made upper triangular by relabeling the points in the state space. So you can think of the directional games as kind of like triangular systems of equations. What we're doing is we're saying that if you have this structure, you can solve first, for values and choice probabilities here, then plug them in here and solve for these, then plug them here and solve for this, and so forth. That's basically equivalent. That's the same approach. That's what we're doing. And of course, this big system of equations will characterize the equilibrium of the game. The MP equilibrium will be given by a big system of nonlinear equations. And if you have the structure, why not use it? That happens in the literature. We found a few examples. These are the corresponding the representations of the state space. So for example, here, this is the tipping and concentration in markets with indirect network effects. Imagine that the market is being gradually filled by two competing platforms. And at some point, on this collection of points in the state space of that model, everybody has either one or the other platform, like Xbox and PlayStations, I think that's what it is. And you can see that if you only allow people to buy, then this is a directional process. John has recently published a paper on tennis. And tennis is almost a directional process. This is a representation of a tennis match. The only problem is that if you're in deuce, then there's this 6 states here, which are all interconnected. So if you run that topological sort, then this space here remains to be non-directional. Well, you can still work with that if you can solve this game as together. All of the states would be in the same block of that nonlinear system of equations. And if you can solve this, then you can then build up the solution in the same way over the rest of the graph. How much time do I have? Still plus? Yeah. Okay, any questions to this? So this process, the generalization of backwards induction, we kind of called in the paper a stage recursion. Please use it if you can. Remember yesterday I told you that there are smart algorithms, and I'm going to continue today. This is not all of them yet. All right, now, can you see the problem? Multiplicity. So I'm solving this nice state recursion. I've I have a DAG, I've partitioned the state space into this stages, I'm solving here, I'm solving this, and suddenly I have a situation like that. And this is what Bertel was talking to you about. These are best response functions in the probability space in this leapfrogging game. And there are 3 equilibria in that one stage. And that's exactly what you just saw in a static model. Now we are kind of partitioning or decomposing the big dynamic model in a bunch of static models. And that's what happened here. Turns out that it's very typical that on the interior points, those orange points in our game, there's multiplicity of equilibria. We actually proven in the second paper, I guess, that there is at most 5. We can have 5 equilibria in the stage. But 3 is typical. Okay, what do you do? So see, you can imagine that you can compute them. And so in order to continue with my state recursion and use solutions in this layer upstream when I solve the upstream points, I have to somehow choose a solution here, right? So, okay, maybe I can write a rule for myself, like equilibrium selection rule, which would prescribe which equilibrium to choose in each point in the state space. Well, but the problem is that if I choose one or the other equilibrium here, that changes solutions everywhere in the upstream. So everything here depends on a solution here. But not just numbers, the number of equilibria, like equilibria sets, depend on what I choose here. And so in general, it's really hard to just look at the game and look at those Bellman equations that I showed you, and write down the list of equilibria that I would like to compute. There's no way. You have to kind of search, and that's RLS, recursive lexicographical search algorithm. That's an algorithm to search for all combinations of stage game equilibria in the efficient way. So if you look at the published paper, we are talking about equilibrium selection strings and solving the game conditional on the equilibrium selection rule. We represent them as strings, and then we write a pretty complicated, we have a subsection on variable-based arithmetics. Okay, and we explain how to work with those strings in such a way that you enumerate all of the equilibria, or that helps you enumerate all of the equilibria. And yeah, if you read the paper, it's pretty involved. Well, turned out a few years later that what we're doing is actually constitutes depth-first tree traversal. Okay, and if you haven't heard about this algorithm before, that's also computer science 101, very simple algorithm on a graph that is a tree. But the problem was that we didn't realize that we had a tree, right? It turned out that this set of solutions to this dynamic game could be thought of as a tree. And let me show you how we can think of that, or how we can build a tree. I'm going to build a graph, or traverse a graph. Now the numbers in these boxes are indices of points in the state space. Okay, and if I just flick back here, these are the indices of all these different points. Now remember that this point is independent. I can solve it before knowing anything about the rest of the game. And each point upstream is dependent on my solutions downstream. So over here, I want to index the points in the state space such that the independent one is here. And the most dependent is on this side. And so I go through my backwards state recursion, and I solve from the back, I solve different. At point 9, I have multiple solutions. Okay, I'll just remember that there is this branching in the tree. There are multiple solutions, and follow the top branch. And there are multiple solutions here, here, and here, and all of these points, they're all interior points. And I just follow the top branch. And when I get to the point number 1, that means that I've solved for one market perfect equilibrium, or for one equilibrium in this game. So the equilibrium in this tree is a path from the root all the way to the leaf. Okay. And so what's the next thing to do? Come back to the last time the tree branched, and then continue extending this second branch. And that's pretty efficient actually, because remember, I'm solving for choice probabilities and value functions for all the players in each point of the state space. And actually the solution that goes all the way to 2 can be reused. I don't have to recompute it. I just have to recompute this last one point that is dependent. Does it make sense? And then we just continue the process by just going back to the last branching that we didn't explore and continuing. And you can see here that there was no branching in point number 2. So this is how the set of equilibria in this particular point in the state space depends on what we have chosen in this point number 6. That's what I was referring to, that, you know, conditional on what you choose as a solution, the rest of the process can change. But you can see pretty easily, right, that we can traverse this tree and extend the branches. And once I've done all of that, you know, I have all of the solutions there, starting here, and all the path to each leaf. The number of leaves in the end is the number of equilibria in this game. Okay? And so we have a theorem that if you can solve a small game, that then you can use the algorithm to combine the solutions into a full set of solutions on the of the dynamic directional dynamic game. And here's the picture. So did I start with the simplest possible extension of a Bertrand game into dynamics? This is 164 million equilibria that we have solved for a particular set of parameters with like 7 points in on the grid of 6.
I think it's 5.
Okay, it's 5. Now these dots here, they represent the payoff for the 2 competitors in a particular equilibrium. The size and the color, I think, both represent the situation where the pair of payoffs is actually repeated for some reason.
It's just in one point of the state space too. Like
Oh, it's at the top of the pyramid. Yeah, these are basically values at the top of the pyramid. Multiplicity is a thing. Now, should we take this to the data? Maybe not. So maybe the model that we've been looking at is a little bit too flexible. But the thing is that, yeah, like I said, we then studied the properties of this model and proved a bunch of theorems, including sufficient conditions for uniqueness. So it turns out that if you force the technological progress to make a step every time, yeah, if you include this equal sign here, so essentially you have to assume that the technology improves even a little bit, but every time period. That, together with alternation of moves, gives uniqueness. Okay. And yeah, there are some graphs to show that alternation generally helps. The number of equilibria is much reduced with the alternation of any sort, deterministic or stochastic alternation of moves. By alternation, I mean that in one period, only one firm can invest. And who has the right to move is an exogenous Markov process. You know, the different assumptions on the technological progress change the set of outcomes quite a lot. And what's interesting is that if you impose that symmetry condition, saying that the value function, the solution for firm 1 is the same as solution for firm 2 when you swap the C1 and C2, okay? And you impose that this is the set of equilibria that you're left with.
Okay.
Symmetry is not enough.
How can there be multiple equilibria with alternating?
There are multiple equilibria with alternating.
They're all.
So, okay, if we look at this condition again, in infinite horizons, if there is a possibility that the system stays at the same place, that gives you the possibility for multiple solutions. It's only if we ensure that the whole industry, the whole state vector kind of moves to a new point every time period. So that we force, for example, in this context, we force technological progress to make a step every time period. Then we can exclude that possibility of having an equation which may have multiple solutions.
Usually sequential games have unique solutions.
So sequential games in finite horizons, yes. Infinite horizon, not necessarily. But yeah, I mean, it definitely helps. So maybe strictly it does not have uniqueness, but just happens to have unique solution for particular value of parameters as well. But we can talk about that. Anyway, any questions on the solution? Yeah. So I'm thinking about the MPE, right? The Markov perfect equilibrium. We haven't tried other equilibrium concept. That's a very good question. We should, and I don't think it would be impossible. So I think what we need for this to work is time consistency. Yeah.
What if the model has time parameter?
Wonderful, it's directional. Because time moves in a very simple DAG.
If you haven't said that, but they're making me probably finite parameter.
Unique equilibrium. The issue, I mean, the intuition is the following. In the finite horizon game, everything is time specific. So by definition, one evolution of time makes all of the values new, unique. And so it's the same as if this condition held. It's like the probability of staying in the same point is 0 because time changes every step. Okay, so I want to do estimation. I have like 23 minutes, right? Not much time. Well, I hope you learn from this that studying the structure of the program is useful of the model. Sometimes the structure of the model gives you very good algorithms. So all right, this is the set of equilibria, and in the dynamic game, we're going to be looking at Markov perfect equilibria, basically the solutions of these two sets of equations. The optimal or inch-temporal optimality, everybody is solving their Bellman equations conditional on their beliefs about the actions of the others, P, and the actions constitute mutual best responses, right? So this is like a whole bunch of logic formulas here. Let's index the set of equilibria. Now, in the estimation problem, we have theta, right? The structural parameter. And as we move the structural parameter, as Bertel showed you, the number in the set of equilibrium may change. And therefore, this K is going to be dependent on theta. The data we have in mind is a panel data over markets indexed with M and time. Okay, and if I want to write a likelihood function, I'm going to think of this in several steps. So first of all, the MLE was going to be given as an argmax over parameter of the likelihood function that depends on the data and the parameter. But as in the static example, we will think of this likelihood as a maximum over equilibrium supported for that level or for that value of the structural parameter theta. Of these likelihood functions that are now specific to an equilibrium. And to denote that, I'm including this equilibrium choice probabilities as an argument to the likelihood. Okay, I mean, the likelihood is going to have a very standard form. We're going to collect, to sum up the contributions, the log likelihood contributions from the points that we observe X and the actions that we observe, collect that over players, markets, and times. Okay. And now I'm going to make a transformation. When we want to study data, we're going to set up the state space such that we observe data on that state space. And that means that I can think of that state space of the model with the iota being the index of different points in the state space. And I can just calculate how many times did we observe, do we have the observation in that particular point iota, just sum up, over times and markets, and how many times a particular action was taken in that particular points in the state space iota. Okay? This is a trivial transformation, assuming that we don't have an observed heterogeneous mean. And so I can express the same likelihood, but now this is summed up over actions, players, and points in the state space. Okay? And yeah, you have to also multiply by the times, by the number of times particular action is taken. What's the data? Well, this is going to be the state space. All these points C1 to C, C1, C to C. On the axis, you're going to have some distribution of the number of observations. and the number of times each of those companies made an investment decision. Just from that, I can calculate CCPs, which I've tried to draw over there on the top. This is CCPs for different actions in different points in the state space. And here comes the kind of the main breakthrough. There are two breakthroughs to make it possible. And so one a clever algorithm and another kind of a refinement of that algorithm. Hope you have energy to learn yet one more very exciting computational algorithm. It was actually published in Econometrics in 1960. Have you ever heard of branch and bound method? Anybody? Okay. The thing you need to know to understand is that it takes two components, a tree, and we already have a tree. And then it has to have a bounding function. The bounding function is the best, it's like an approximation of the best possible objective on a subset of the solutions. Let me get into that. Think of this partial likelihood. I want to calculate the likelihood of the data, but only a subset of states in my problem, okay? So I'm going to take iota only from some subset. The data lives on the state space of the problem, as we just said, right? So I can always do that. Now think of me computing those equilibria and traversing the tree. I'm going to do the same thing as before, but now I know choice probabilities in points 14, 13, all the way to 10, and I have data that lives on those points in the state space. So I can calculate the partial likelihood, partial log likelihood, only for the points which I've computed the solutions of. Okay? And then there will be branching. And what's that? You know, these are three equilibria in this points 9, and I can add data in point 9 to compute three different partial likelihoods. And you can see that that top one is kind of more promising. All the numbers are made up in this example. And so maybe we can continue traversing that branch, which looks more likely in the data. And we can continue doing that. And once we get to the first, once we computed the first full equilibrium, so we got to the last point in the state space, we've included all of the data along this solution. And so this number in the end is exactly the likelihood that I need to compute. It's now the partial likelihood over all of the data. So it is the likelihood of that equilibrium. Okay? Now think about this. So I'm about to extend this branch from the blue point here. And my partial likelihood is minus 10.1, and my record is minus 11.2. If I extend the branch and compute another choice probability, and I use the data in that last point to update my likelihood, the likelihood that I already have, the partial one, will only reduce, right? Just because I'm adding more data. I'm adding more data, I'm adding another component of the log probability, another negative number. And that means that this will only go down as I add data, and yet it's still above minus 11. Okay, so let's try. Okay, and we got a new record there, say minus 10.2. But over here, it's already minus 13. If I add more data, that number will only go down. There's no point of extending that branch. I know that the likelihood will be lower. And so I'm not going to do that. How about here? I don't need to extend any branches stemming from this point because I already know the likelihood is too low over here compared to the one that I found. So I'm not going to extend that branch. I'm not going to extend a lot of branches. But sometimes maybe something else is promising.
That's a question.
Oh, yeah, question.
Yes, why we don't just do
This one. It's a good point. That's a mistake. We should have used the greedy strategy and picked that. But I wanted to have an example where it switches. But the point is that if somewhere else in the tree you find some promising likelihoods, you will extend them. And so you will find the more likely equilibrium path. Because you're doing this systematically. Yeah.
Sorry, no, we don't. Promise.
Promising. So this partial likelihood anywhere here. Okay, let's look here. This partial likelihood includes the data from here all the way up to here. And this minus 9.8 is still above minus 10.2. So even though this number will go down, maybe it will end up higher than minus 10.2. And that's what happened. Oh, that didn't happen. Didn't happen. But maybe this is still promising, right? It still may end up above the 10.2. And yes, it does. And now we have a new record. Another question?
So it has to be then this that you really have instances of the game where the entire all the way to the end was played.
If you don't have data somewhere, that means that the likelihood is just zero there, right? And so this will not update essentially, they will stay flat. So
Can you estimate the game even if you have switched the red point?
absolutely,
Find out the
yeah,
line of it.
yes. Yeah. Okay, that's branch and bound. So the method is pretty ancient. It was developed for solving integer programming problems. And the main idea is to be able to throw away parts of the set of solutions efficiently by using this bound. I'm running out of time, so let me just run through this. There is a much better way to do it, which is based on non-parametric likelihood. And let me just talk about this graph. This is again the state space. And we are doing this branch and bound thing. We're computing partial likelihood, and it declines as we add more and more data, right? So we start over there with no data, then add data from one point in the state space, and then more and more. And these black lines actually show likelihoods of all of the equilibria. This is full enumeration. You can see that, you know, the likelihoods that we're interested in, the ones that have all of the data included, they're here. This is the full set of likelihoods calculated on the full set of equilibria. The most likely one is here. First point to make is that greedy strategy does not always work, right? So this best likelihood was not best along the way. You really need to do that branch and bound procedure. But then there is a way to calculate this blue line, which is basically a likelihood computed on the CCPs, on the frequency-based CCPs directly from the data. You can show that that blue line is always above any likelihood from a parametric model. This is an algebraic fact. It's not statistics. But the fact that it still declines allows us to use it instead of the flat line as we did before to forecast where the likelihood of the data will end up. In fact, if I use that line, you know, at any point, I would use the rest of the blue line and attach it to my current estimate. You know, all of this computation down here doesn't have to happen, because I would stop not when reaching the flat kind of comparison between the current record and where I am now. I would have this way to make it more powerful. There was a question?
You just mentioned that like the final result as you get a red line, what's the most optimal?
Yeah, over here.
On the path. So like I just wonder, how could you like optimally pick out what's gonna be the final optimal result at the end without like no risk going through this like trial and error?
Branch and bound. That's the answer. So you can't trust the greedy strategy of choosing the best on every step, because if you chose the best on every step, it just happens to be down here in the end, because that equilibrium that starts looking really well then becomes not very likely on other points of the state space.
So like it's just like a iterative process, but trying out what's the next best no, by means of comparing
This partial likelihood. Okay, let me make this point. Now, this is a likelihood based on the frequency estimates of the choice probabilities. It's non-parametric, does not depend on any model. But the thing is that it will approach the true likelihood if the model is well specified, correctly specified, and if we're not too far from the true value of the parameter. It will just, this is now statistics. It will be closer and closer as we increase the sample size. And that means that I'm actually skipping most of the computations now. This branching bound with non-parametric bounding function allows you to essentially zoom in onto the most likely equilibrium very fast. And so sample size helps in both statistical and computational efficiency. And that's the point. Okay, let's jump to the Monte Carlo. We have 9 minutes. Here's the idea. So we're going to be using the leapfrogging game. We set up some parameters. We start every estimator with the two-step CCP as a true. This is kind of the best starting value that you can think of. And we will have 3 cases. We will have the case that everybody kind of hopes for, a single equilibrium in the theoretical model, and then by assumption, the same equilibrium played in every market in the data. Then we will have this intermediate case where there are multiple equilibria in the theoretical model at the true value of the parameter. But, it's just, we may or may not know about it. But still single equilibrium is used to generate the data. And then finally, we can have multiple equilibria in the data by allowing different markets to play different equilibria and generate data from different equilibria. Okay, I have to go quickly through this. In the first case, single equilibrium in the data and single equilibrium in the model, everything works. Big table, the true value is 3.5. All the methods are kind of getting there with a very small bias. The estimators that are supposed to deliver you maximum likelihood when they converge, NPL, EPL, both of MPACs, they're slightly different formulations of MPAC. Let me not go into this now. And this nested RLS, the NFXP method with full solution, they all deliver pretty much the same results. So the methods which were supposed to achieve maximum likelihood efficiency do that. Now let's look at these 2 lines on the bottom first. This is the operator from choice probabilities to choice probabilities that Victor uses. And this is basically a collection of Bellman equations. If you see zeros, that means that at the estimate, the equilibrium is achieved. So at the estimated value of theta, we have equilibrium. And that happens for all the methods which are actually enforcing equilibrium. The two-step does not. Right? The two-step assumes that the data represents the equilibrium. Theoretical equilibrium is not enforced. 3 equilibria, the true value of the parameter. The data generating equilibrium is stable. This is very similar to what Bertel was talking about. What we see here, well, MPAC starts having some convergence issues. Why is that? That's because these equilibria are separated, right? So enforcing that constraint may not be as simple. What else?
What about this log likelihood shortness? That?
Oh yeah, the log likelihood shortage is basically, these are averages over all converged runs. And the log likelihood shortage is the difference between this estimator and the best estimator in terms of likelihood in different runs. So this is to say that NRLS was best in every run, right? And MPAC was lacking in some runs, and EPL and NPL. See, NPL is really sometimes loses, right, the race to other estimators now in presence of, oh, I'm sorry, I switched in presence of multiple equilibria. Okay, this is just to check that it basically confirmed in the paper by Victor and Gergavir and Marcoux, which really investigates when NPL doesn't work. And a sufficient condition to break NPL is to generate data from an unstable equilibrium. This is kind of a theoretical interest. I don't know if any data in reality can be generated by an unstable equilibrium. Now, let me skip that for now. If we have 9 equilibria at the true value of the parameter, and see it's near cliffs. The cliff is the thing that Bertel showed you, the situation when the equilibrium that generated the data disappears when the structural parameter changes a little bit. And this is really hard now. So NRLS works fine. MPAC just fails to converge a bunch of times. EPL and EPL deliver an equilibrium, right? So they do enforce this equilibrium conditions. But if you look at these 2 lines here, we are showing the maximum absolute deviation in choice probabilities over the state space. And we also calculate the Kullback-Leibler divergence between the distributions of trajectories implied by different equilibria. The point is If it's zero, close to zero, that means that the estimates corresponds to the equilibrium that generated the data. Okay. When you see non-zeros, like over here, for example, that means that the method pinpoints an equilibrium, because of this, but it's a wrong equilibrium. So, for example, here NPL is in one point of the state space is 86 percent point off in the choice probability. So that's the situation which Bertel also showed when an equilibrium disappears and it's impossible to put the choice probability at the right value. This is average over 100 runs. So this can be illustrated by this figure now. It's kind of a flat version of the cliff. Now, imagine this is the theta, the structural parameter, and imagine that we put a dense grid on theta. For every value of theta, we've computed all equilibria because we can, and then calculated likelihood for each of those equilibria for all different values of theta, and connected the dots. And so what you're looking at is actually an equilibrium correspondence in the likelihood space for a given sample, given generated sample. As we move theta, the likelihood of this different equilibria changes. And if we move it from 3.5 to 3, all of this equilibria just disappear. They don't exist anymore. They're not supported for the different value of theta. The true likelihood is an upper envelope of this correspondence in exactly the same way that Bertel showed for the static game. And you can see different estimators where they land. The two-step estimators are off any of these lines because they don't enforce equilibrium. NPL and EPL in this particular Monte Carlo run end up over here. They're on the equilibrium, not very far from the true value, but it's the wrong equilibrium. A bias is possible here just because of the non-identification of the equilibrium. And then NRLS kind of on the top, there's it. Usually, yes. If I click back here, that's the same picture for that previous Monte Carlo. And remember, MPAC had problems converging. Well, MPAC is shown by these little squares. If you really look closer, there's a square. So MPAC did deliver a maximum of this particular equilibrium. It's just local maximum. And it's really, it got lost in the woods, so to say. It could not ensure the equilibrium conditions around the true value of the parameter. I really have to stop, but let me still talk a little bit about this graph. This graph shows you the Chi-L divergence, the one that we use to measure the distance of the estimated equilibrium from the data generated equilibrium. And so here you're looking at the histogram of those Chi-L divergences, but the histogram is special, it's on a log scale. So this is really, really small compared to this. Now the data generating equilibrium is kind of to the infinity on the left. You want this measure to be as close to the left as possible. Different estimates. And these vertical lines show you other equilibria supported at the true value of the parameter. If we look at this plot again, you see there's two lines actually here. And so at the very top, there's this equilibrium, which is pretty close to the one that generated the data. This Chi-L measure is 10 to the power 3. And these other equilibria are basically, this one, and so forth at the true value. Well, the point to make here is that it seems that the NRLS really does much better in identifying the data generating equilibrium compared to all other methods. MPAC sometimes kind of is not distinguishing between those two top ones, but pretty close, but the mass of the Monte Carlo is over. Okay, let me jump. Oh, one more point. I'll take 2 more minutes. Sorry. One more point is time. Can we actually do it? Well, this is the case with 2,500 equilibria at the true value. And it takes 10 minutes to just run RLS once, to compute all equilibria for one value of structural parameter, 10 minutes. This is the average time to estimate the parameter, 4.7 seconds. Why? Well, because of the smart algorithms, right? So this is the branching bound in action. And now this time is actually comparable to the other estimator. So, of course, it depends on how informative the data is between kind of throwing away unlikely equilibrium or not. Now, let me look at this final simulation where we are, when we have 3 equilibria in the data. So what does it mean? It means that we have markets in defined groups, which are playing different equilibria. And we're estimating structural parameter, which is the same across all of these groups of markets. So I'm just showing you the results for NRLS. And the question here is this KL divergence. Did we in this given groups, did we pinpoint the equilibrium that generated the data or not? And the graph is pretty much like this, right? These are these 5 different groups of markets playing different equilibria. And each time the estimator could differentiate between the equilibrium that seemingly generated the data and all other equilibria that exist at the true value of the parameter. And the same picture essentially holds when you have 20,000 equilibria at the true value. Okay, I think I can stop here. Thank you so much for attending the summer school. It wouldn't be without you.
Winter.
Oh, winter school, I'm sorry.